Our next speaker is Dr. Yog'in Tu. He is the director of NASA's Ames Research Center, a center that operates, among others, two of NASA critical infrastructure assets, the ArcJet testing complex, which is a must when you want to return safely to Earth, and NASA primary supercomputing facility. Dr. Tu earned his bachelor degree in mechanical engineering from University of California, Berkeley in 1988, and both his master's degree and doctorate in aeronautics and astronautics from Stanford University. Dr. Tu began his career at NASA Ames as a research scientist conducting CFD research on the steady and unsteady aerodynamics complex aircraft configuration, and since 2 years he is the center director. Dr. Tu received the NASA Outstanding Leadership Medal in the year 2000 and the Presidential Rank Award for Meritorious Executive in 2009. And he will talk to us about supercomputing role in the new space area. Dr. Tu.
Okay, thank you. Well, it's great to be here again and have a chance to talk to you. This field actually hits a little closer to home for me. As mentioned, I started my career in computational fluid dynamics. It was in the early stages back then. Even some folks believed at some point we would be able to replace testing, flight testing, and wind tunnel testing with computers. And of course, we realized that that wasn't never going to happen. But the complementary nature of computing, the ability to model and simulate and compute has really changed the way we design, we conduct science, and many other fields. And we talked about sort of the emerging area of big data as well. And so this is an area that we feel will really potentially continue to advance. When I started, most of the work was being done on supercomputers. Supercomputers back then probably had about the same power as everyone here is carrying on their phones today. And then now we've, of course, advanced quite a bit. And there are new computing architectures and ideas out there, and I'll touch a little bit upon that. But you really can't talk about computing and what computing can do without really trying to at least describe some of the uses that we have for it and what the critical needs are. So I'm going to start with that, and I'm going to spend a little bit more time on those applications. So we have within NASA a very diverse set of high-performance computing requirements. Much of it stems from our scientific work. Much of it stems from the engineering work that we do, and also from the actual in situ or real-time analysis that needs to be done. And so we have sort of three types of computing that we do today in advanced computing. We do what we call high throughput or capacity computing. This is where you're trying to run as many computational jobs as possible, exploring a parametric space, exploring a design space, for example. And so really the efficiency there is about how many runs can you make, how many parameters can you vary, how many variables can you change. Then we have those class of computing that we call capability computing or leadership computing. And that's really pushing the envelope of what we understand, solving the fundamental equations of engineering, of science, and really trying to basically add to the knowledge of the physics, the chemistry, the biology of what's going on. And that's another class. And then finally, we have this time-sensitive or mission-critical computing that we have, where, for example, when the shuttle was operating, certainly after the Columbia accident, we had to have supercomputing available to basically do analyses if we saw damage or saw a problem with the thermal protection system. We had to have the ability in real time to do as many calculations as possible before making the decision to bring the shuttle back. And so those are the kind of real-time computing needs that NASA faces as well. It requires a certain reliability and uptime and availability of computing that you don't get typically with the research and the other types of engineering computations, but it does put a strain or a constraint on the computing systems. So let me next go to some examples of where we use high-performance computing. What you're seeing here is simulation of rotorcraft, helicopter blade interactions, and really it's a very, very complex flow field. We're looking at color contours that represent pressure and vorticity and the interaction of the structures with the fluids. And we're really getting, and then you can also see the acoustic waves that are generated by that. This level of computing is quite intense in terms of the number of grid points required, in terms of the computational power required, and really represents some of the most challenging fundamental fluid dynamic computations that are being done today. Another example in the earth science area, this is an ocean model. And what you're looking at here, let me start the other video as well, is the surface of the ocean velocity. And the other video is, oops, I'm sorry. The other video is not actually starting, so let me go back. See if I can go back. Okay. I'll try this one more time. I think I'm straining the computing system in the here. So the other video would run, but basically what you're looking at is surface velocity of the ocean, simulated and also initiated by satellite observations, but then run for some period of time. The degree of resolution here is 1/48th of a degree resolution. And the time scale is basically 6 hours every second. And so what you're seeing here, you can see the flashes there are the tidal movements that occur on the planet. But really, with this type of simulation, we're able to couple that with atmospheric models to really look at the whole Earth system and the changes that occur. Getting to some space applications. Here's a simulation of the new SLS launch vehicle on the launch pad and the first 1.2 seconds of launch event. We're very interested in the ignition overpressure and the pressure waves that may impact the vehicle and have potential impacts on the payload. We're also interested in the flame trench itself and whether it can contain the gases and the energy. And then you see in the middle picture at the bottom there, basically the adaptive grid and how the grids are being refined as the physics warrant in terms of doing this type of computational simulation. Here is a computational simulation of solid rocket booster separation. This would occur at approximately Mach 4. And what we're interested in here is to ensure that the solid rocket motors don't recontact the core stage, obviously, and cause damage. Again, it's a very complex simulation, and it is something that is very difficult to do in a testing environment. So here's where you're seeing we can do some limited tests. We obviously will have flight test data when it's flown, but it's a case where you really have to rely initially on very complex computational analysis to understand the flow physics of what's going on. And my final example here is a parachute. This is a 60-foot or roughly 20-meter parachute, supersonic parachute, that would be used, for example, for heavy mass landing on Mars. This is I believe about 3 to 4 times larger than the current largest parachute that was used to land Curiosity. And this parachute, again, is supersonic. So first of all, due to its size, we have limited test facilities that can actually handle this size of parachute for testing. And certainly those 1 or 2 facilities that can handle the size will not be able to run at supersonic speeds. And so really you need to, again, combine the testing that you can do and the computational modeling to understand the flow physics and understand and make design changes to affect that. So let me get back to, these are applications of advanced computing. And really today, the heart of the engine for advanced computing for NASA is our supercomputing facilities. But we are very interested in looking at what are the other types of computing that are on the horizon for us. And so specifically, we have a strong interest in the area of quantum computing. We have a quantum computing device at Ames that I'll talk about, one of the largest in the world. And we are doing research on it. And I've been asked many times before, is it real? Is it something that we believe will be realized soon, where quantum computing can make a huge impact? The answer is we don't know. The answer is we need to do the research, in my view. The challenge is that the maturity of the technology and the maturity of the knowledge of how to use that technology is still relatively low. And so it's something, I'll talk a little bit more about, it's something where, again, for an agency like NASA, that's a mission-oriented agency, we can't afford or have the resources to just fully invest in a speculative research area so early in its stage. So we look for partnerships to do so, and I'll talk a little bit about that. So what does quantum computing bring to us or what do we think it'll bring to us that really sets the way for the future? Clearly, one of the areas of big promise for quantum computing is the ability to handle large optimization problems. So many of the applications we've talked about explore design space, and with classical or traditional supercomputing, the number of variables you can have in your design space is very limited. At some point, the problems will not scale to the point where you can reasonably solve them with any supercomputer in a reasonable amount of time. So the idea behind quantum computing, and I've asked the people who put some of these charts together for me, don't put any equations up for me. So this is the one thing they did for me, was a graphic there to really emphasize what quantum computing does. And the principle of quantum computing, to be able to handle multiple states at the same time, is the ability to tunnel, and in tunneling, the ability to find optimization or have a better chance of finding optimized solutions that you don't get with classical computing. With classical computing, you can often get stuck in a local optimization, where with quantum computing, the promise is that you can really, truly find a global optimization. And so what are the types of problems that NASA is interested in that we feel quantum computing could help us solve? Certainly data analysis and data fusion. Air traffic management is a large data problem. There are 5,000 airplanes in the sky at any given time, just over the US, and trying to do trajectory optimization in the face of weather, in the face of other issues within the system, become a large optimization problem. Mission planning, scheduling, and coordination, particularly in areas of unknown environments. Those are the type of problems where strong optimization needs are. Anomaly detection, decision making, V&V for optimal sensor placement, and others. So these are the type of problems we feel quantum computing has the promise to address. So at Ames, the system we have is a D-Wave hardware system. It's a quantum annealing device. It's not typically known as a universal quantum computer, but it is a quantum device that exhibits the quantum characteristics we're looking for of superposition and tunneling. And so the device is actually built by a company in Canada, and we have entered a partnership, in this case with Google and USRA, to have one of the largest systems sited at Ames. The system started back in 2013. With about 500 processors, or what they call qubits. It's been increased to about 2,000 now. It is operating at near vacuum, also very low temperatures, 15 millikelvins, which I think Charlie has mentioned once is colder than interstellar space. Magnetic shielding is required. And so it's basically the container that you see on there is a Faraday cage, and it basically keeps the shielding down to a level of 1 nanotesla. Vibration is a big issue, and we're in California. All of our buildings are built to handle vibration and to move with the earth or to roll. And so for this computer, we had to actually put it on a pad that was isolated from the building and reached all the way down to the bedrock. And so you can see some of the other statistics there, very low power usage. And so this is a research device right now. This is something we are looking to see when and how we can get meaningful applications from it. Some people have asked me also, when do we think there will be a real application that will demonstrate a significant speed up using this type of device over a classical supercomputer? We would estimate probably between 3 to 5 years. And so that's kind of a rough estimate, but we need to see what kind of breakthroughs we can do in research in this area. So finally, just to wrap up, these are the kind of missions, the kind of applications, and really quantum computing, we don't feel, just like the supercomputers of today, are never really going to replace the tunnels, wind tunnels, and other testing abilities. We don't believe quantum computing will replace supercomputing that we think of today. It'll complement it. And in fact, the one reason the partners were interested in citing this device at Ames is because we have one of the largest supercomputers, and really it may take a supercomputer to help analyze the data that comes from a quantum computer. So the two will work hand in hand. Another way to think of it is a quantum computer can be thought of as a node off of the supercomputer, specifically designed to help solve problems that require optimization. Thank you very much.